and I have the pleasure of introducing John Gabrieli. John is the Grover Herman Professor of Health Sciences and Technology at MIT and an investigator at MIT's McGovern Institute for Brain Research. He uses neuroimaging and behavioral tests to understand how the human brain powers learning, thinking, and feeling. And for the last couple of decades, John has sought to unravel the neuroscience behind learning and reading disabilities and ultimately convert that understanding into new and better education interventions, a sort of translational medicine for the classroom. In 2018, John and the MIT team Integrated Learning Initiative announced a $30 million grant from the Chan Zuckerberg Initiative. And this is a collaborative effort with the Harvard School of Ed and Florida State University called Reach Every Reader, with an aim to make significant progress on the crisis in early literacy, including tools to identify children at risk for dyslexia and other learning disabilities before they even learn to read. John has many awards and distinctions and has been a fierce advocate for individuals with dyslexia and a mentor to leading experts in the field. And we are thrilled and honored to have him with us here today. And I will turn it over now to Professor Gabrieli.
Thank you, Teresa, for the gracious introduction. It's a pleasure to be attending this meeting of the California Reading Coalition. I congratulate Todd Collins for leading this group, but you're an inspiring group. The comments that you have, you're here now because you care that so many more children need to be able to empowered by learning to read effectively so they can do so many other things. So I've always been impressed by the fragile power of the human brain. It endows us with the capacity to think and see and speak and hear language. It has the brilliance to invent, print. Oh, somebody's moving faster than I am. Sorry, if we can say thank you. And at the same time, it has, for every strength it has a fragility. If it can have emotions, it can have anxiety or depression. If it can brilliantly invent spoken language made visible through print, it can have a risk for dyslexia or reading difficulties. The next slide shows my sense of that every infant on this planet is born into a world where their environment and their genes will make life easier or harder to navigate. We were never created to be readers. We were created to speak and hear language. That's in our evolutionary history. Print is a recent cultural invention, and maybe that's why so many children struggle to read, but we made it a central aspect of education and citizenship. And the next slide, please. We know that so many children struggle in various ways. Today, our focus of discussion, of course, is dyslexia, about 10% of children, but ADHD, autism, many children need support of special education. Poverty is another reason why a child might be behind in reading, about 20% of the population, 50% free and reduced lunches. Next slide, please. Next slide, please. Thank you. And now we have neuroimaging, which allows us something we could not do before, which is to use something like an MRI, which you see on the left, to show us gray matter structure of the brain, anatomy, white matter structure of the brain, and the functions of the brain through functional MRI. Next slide, please. I'll come back to that. And the other thing that we realized is that in the United States, the comment is people estimate 20%. We can talk about that, but 10 to 20 is depending on how you define it. We also know that in the United States, this is a map of all the nations on the globe, and purple is the US. Everything shown in blue are countries that have less inequality in terms of income, in red, more inequality. And you can see that the United States is not only a leader in world wealth, but a leader in income inequality across the population. So we know our educational system operates in that context. Next slide, please. Now, spoken language occurs naturally, brilliantly, beautifully between a parent and a child. They spontaneously make sounds with one another, and the child learns to speak under the vast majority of circumstances. But in the next slide, you can see that we know reading is the opposite. It's not natural and spontaneous. It's formal, explicit, intensive instruction. It's kind of a boot camp that kindergartners and first graders go through, and then for the next couple of years in school, as they go from learning to read to reading to learn. The next slide, please. And we know there's all kinds of different numbers. 10%, 15% of children, there's no sharp dividing line. All those children can use support and help to become effective readers on their behalf. The next slide, please. We know that the best understood cause of dyslexia is a weakness in phonological awareness, the ability to recognize and manipulate parts of spoken language. But reading is a very complicated process. It involves many things, and it can involve visual processes, auditory processes, thinking processes. So there's many things that can conspire to make reading difficult for a child. Next slide, please. Now, neuroimaging has gone through two phases, and I'll take you briefly through a couple of them. The first, just to see what our brain differences associated with dyslexia, and to see how does the brain change with effective remediation. And then more recently, we've been trying to think harder about how to use brain imaging to address questions that are relevant to parents, children, educators, things like diagnosis, early identification. Next slide, please. So sometimes people have asked, how do children like being in a scanner? We've scanned hundreds, perhaps thousands of children now. This is a spontaneous note we got from a study at Stanford, where I used to work, from a 9.5-year-old girl. And she draws the noisy scanner. And she writes to the graduate student who worked with her, "You've let me have more fun in 3 days than I could have in any other place. Just think of it, I'm playing a game where at the same time I'm a research guinea pig. You could take a couple of points for spelling if you wanted to. And who knows, I might help someone else my age if they have any brain problems while still earning money." All our research participants get a very small payment. And what do you think beats that? Nothing. It's a beautiful sentiment of a child. Next slide, please. So in the study done in California, we saw children who are typically reading or children with dyslexia, about 20 in each group. You can see that the reading scores are lowish, as you would expect in the children with dyslexia. And in the next slide, you could see that they went through an intervention program. At the start, the DYS shows you the children with dyslexia, and you can see the before and after. The dark blue is before, the light blue is after. And that these children had some gains in word reading ability, some gains in non-word decoding, so some benefits from this intervention. They're still below the typically reading children, but the intervention helps. The next slide, please. And while they were in the scanner, we looked at their brains, and we compared two conditions. In one condition, they had to decide whether a pair of letters was the same or different. So was P and P the same? Yes. Was D and M the same? No. The condition we were really interested in is what happens when they have to think about sounds that go with those letters. So here, they have to think of the name of the letter and decide if they rhyme. So G and K end in different sounds. T and D end in that same E sound. And what's happening in their brain as they're linking letters they see with the sounds of the names of the letters. The next slide shows you the differences. The top row are typically reading children. Left is left, so that's the left hemisphere, which is dominant for language and dominant for reading in skilled readers. And you can see 2 points of activation, one towards the top, which is something like Broca's area, and one towards the back, something like Wernicke's area. And if you look at the dyslexic children, you can see that they don't have that selective response in the back of the brain. And you can also see that the response in the front of the brain is somewhat different looking as well. Now, what we all want to do is help children do better in terms of how they read. So the next slide shows you the same things, but viewed from the side. So here's the typically reading children. What's circled are the spots you saw before, engaged when they thought about letters and sounds. The differences in the children before they got remediation in the study, and the absent posterior activation circled in blue. But look what happens after the remediation program. There's a growth of activation in those same dyslexic children in those areas where they had been showed reduced response in the brain before. Now, we thought in 2003, when we published this is exactly what we want when in terms of intervention and support. We want a child to engage those brain systems that typically reading children do. And we do want that in some sense. But the next slide, and we called the changes in the left hemisphere normalization, being more like typical readers. And the next slide is, one slide, back one slide. Thank you. And in the right hemisphere, we saw, though, a ton of growth of activation. So we call that compensation. We said there's something going on there to help these children do better. But the next slide, thank you, shows you another study we did. And in this study with Fumiko Heft, what we did is we looked at children, did brain imaging the first time, and then asked, how are they reading 2.5 years later? So the top row, you see that in the black X's are the typically reading children, reading well the first time and reading well the second time. In the bottom in red and blue are the children with dyslexia. And you can see that they fall into two groups. The children who are in blue don't make much progress over the next 2.5 years for single word reading on the left or for comprehension on the right. The children in red start off just as poorly in terms of reading skills, but you can see they have a much sharper line going up. They've made a lot of progress over 2.5 years. So the next slide shows you this interesting finding, I think. Next slide, please. What's the difference in the brains of the children who will make big progress over the next 2.5 years? And it turns out that's in the right frontal cortex. You can see the activation on the left, and the right panel, every red dot is a different child. The more they engaged this area as they processed print, the more gains they would make in the next 2.5 years. So this sent us a different signal that the most important changes in many children might not be normalization of the left hemisphere pathway, but the engagement of an alternative pathway in the right hemisphere. And the more the child used that, the more progress they made over the coming years in reading. Next slide, please. So now we think that right hemisphere story that we had somewhat ignored might be almost the biggest part of the story for most children with dyslexia who make the most progress. Next slide, please. Now, there's a paradox that many of you know and think about, which is that we talk about early reading as learning to read, and then after the third grade or something, reading to learn for the rest of one's academic and citizenship life. And we know that that interventions that are focused often on single word reading, and where there's research evidence that they actually work for many children, not every child all the time, but for many children. We know they're most effective in kindergarten and first grade. But in many clinical settings, in many schools historically, although I think this is changing, often the schools, for various reasons, or clinicians even, will wait until a child is in third grade or something like that, where they're so far behind, they're certain that the child has dyslexia. But by then, the interventions we know that are most effective for single word reading usually have lost their effect. So it's so important to identify early through screening and other things that we can do. All the research supports that perspective. The next slide, please. So what are the best behavioral predictors in early identification? Measures of phonological awareness, and I'll show you an example. Rapid naming of even things like objects or knowledge of letters. The challenge with early identification, it tends to over-identify, which is still better than under-identifying, but it's something we want to get better at. And the next slide, please. So we did a study in collaboration with Children's Hospital and Harvard, looking at children before they received instruction in school. In Massachusetts, reading instruction begins around Thanksgiving of kindergarten year. So we saw children who were in the pre-K, end of pre-K, the summer before kindergarten, or the first month in kindergarten before reading instruction. The next slide shows you that we screened a lot of kids in 19 diverse schools. We brought in 180 for detailed brain imaging and other analysis, and then followed these children for a couple of years in school. The next slide. There's a reminder to you of gray and white matter in the brain. So gray matter are the neurons, white matter are these myelin sheaths that surround the axons, so signals can go quickly to distant parts of the brain. The picture on the right, which is a cross-section to the brain from that you might see if you were looking at somebody's face, you can see there's a ton of white matter in the brain. And that's the white matter is the superhighway of information processing. It connects different parts of the brain to do almost everything that's sophisticated and brilliant about the brain, like language, thought, and reading. The next slide, please. So we can use a method called diffusion tensor imaging to characterize white matter properties. We inferred from the movement of water in the brain. Next slide, please. And so this is a cartoon of the myelin sheath that we're looking at, the white matter. The next slide, please. This is actual white matter. The brain has so much white matter connecting different parts of the brain, the sort of internet of the brain. The next slide, please. And our research has ended up focusing on something called the left arcuate fasciculus. It's a white matter pathway that connects the two key language areas of the brain, Wernicke's area in the temporal lobe and Broca's area in the frontal lobe. If you had to pick one white matter pathway that was most related to language, it's definitely this white matter pathway. The next slide, please. And we could use the movement of water to infer where these tracts are and what their properties are. I won't go into detail on that, but it's a useful method. In the next slide, shows you the kind of picture we can get to look at, to map the white matter organization in an individual's brain and in which way the fibers are running, up and down, front to back, or left and right. The next slide, please. And we go to the next slide after that, thank you. And what we found in adults is that the area shown in black here in the left hemisphere, exactly around that arcuate fasciculus that connects language areas, had what we understood to be reduced strength of connectivity in adults with dyslexia. Next slide, please. And then we gave these kindergartners, these pre-K and early K kids, tests of phonological awareness. So, for example, many of you know these things, but these kids cannot read yet, so you have to test them for pre-reading skills like phonological awareness. So you might say the word bold, now say bold without b, and they should say old. What do these two sounds make together? T and oi, and they should say toy. And if they can do that well, they have strong pre-reading phonological skills. The next slide, please. And we looked at these different pathways, again, before any teacher has given them any reading instruction. And the next slide, please. What we found is this, and I'll have a simple picture in a moment, but these are the raw-ish data, which is that the better these children did on pre-reading skills, the stronger was this pathway and the bigger was this pathway. So the next picture gives you a simplified view of this. And what shows you is a child who had poor phonological awareness, and that was her arcuate fasciculus at the top there. And when we looked at her in first grade, she was a struggling reader. Somebody with a larger and more strongly connected tract, arcuate fasciculus, was a good reader at the end of first grade. So these things related to their reading performance in later years. Next slide, please. And my colleague, Nadine Gabb, has shown that if you look at children who come from families with a history of reading disorder, about half of whom statistically will struggle, not all of them, but about half, in the very same pathway in the brain as infants, she could detect differences on average in infants who come from families with a history of reading difficulty. So the next slide, please. So we think of often as genetic influences on dyslexia, and they certainly are some that it's familial. There's some genes that have been identified, but we know there's environmental influences as well. And one of the biggest ones that we've documented is conversational turns. How often an adult caregiver or a parent talks back and forth with their infant or preschool child. The next slide shows you the finding that if we look at children, these are not children with dyslexia, they're way ahead, these are 4-year-olds. The more often their parents talk with them at home, the stronger the connectivity in exactly the same pathway. So the genetics affects this, but the environment affects this as well, in terms of the brain developing this language connectivity that's associated with better reading and better language skills. The next slide, please. Now, one of the things that we like to do is try out different kinds of interventions. Summer is an ideal time of year to do it. We're not interfering with the school year, but we are giving extra intervention and support to children who the school identifies as struggling readers, and we can look at their characteristics before and after. So here's a study we did in collaboration with Linda Mood Bell. And we had a tiny school at MIT that we ran in the summer with Joanna Christodilo as my collaborative partner. The next slide, please. So these children got for free 65, we tested 65 first and second graders. 40 of them got 100 hours of small group intervention in the summer across 6 weeks. 25 were randomly assigned to be waiting list controls. That they did not get the intervention in their summer, they're a control group, but they all received Linda Mood Bell invitations for lessons in the fall. So everybody got it sooner or later. And we worked hard to get a diverse socioeconomic status sample, children who came from more supported environments, children who came from less supported environments. And we looked at brain structure before and after. So here's what we found. Next slide, please. There's a scary looking graph, but let me tell you what this is. The zero line is the scores. These are children in first and second grade. So the weighting control group are the children who are poor readers. And the fact that the bars are going down from zero on a series of reading measures tells you that across the summer, these children who were in the study because they were behind on reading, their scores went even down even more. Sometimes people call this summer slide or summer slip, summer melt, but it's especially pernicious for children who are already behind on reading, right? The summer is pulling them back and they're already behind. The next set of bars are the intervention. I'm sorry. Are the children who got intervention. And you can see that they're at zero. We wish we would see a higher number. It's still better. They're still better off than children who didn't get the intervention. But within those children, we saw two groups. One group were the non-responders whose bars are pretty low there. They didn't get much benefit from this program, even though they came in and did their best. The last group on the right did get a striking benefit. Their scores went up on multiple measures in reading. So we had this mysterious divide between children who benefited very little and children who benefited substantially. And we think that's a really important thing to understand. Which program works for which child? And in current practices, we sort of, we trial and error. We try something, it doesn't work, we regret it. We need to know upfront so that a child, never gets an intervention that's unlikely to work, but gets one that's correctly tailored for that child's needs to become a better reader. So the next slide just summarizes what was the best predictor for us in this study in terms of how children did. The best predictor in this study was the children who came from lower income, less educated families, lower SES families. They showed the most benefit in the study. And the next slide is the last slide. This is just a reminder for me, sorry, it's almost the last slide, that we talked about white matter before. Now we're going to talk about gray matter in the brain and the cerebral cortex. Next slide, please. And we can take pictures of the brain and then measure the cortical thickness of the brain. The next slide, please. And this is showing you the raw MRI that we measured that way, going from ear to ear, and where we measure or quantify the gray matter in the brain. Next slide, please. And here's what we found. On the left are the brains of the children who did not receive the intervention. Their brains did not change across those 6 weeks in the summer. In the middle are the brains of the children who did not respond to the intervention. They did not, their reading scores did not go up and their brains did not change in terms of anatomy. And on the far right is what we want to do. Those are the children whose reading scores went up. And everything you see in red and yellow are areas where their neocortex of the brain got significantly thicker. So that effective intervention changes brain anatomy. I mean, all effective education changes the brain. The mind is what the brain does. And if we want to change the brain and help a child have social emotional growth, cognitive growth, and so on, that has to always come from some sort of physical change in the brain. Next slide, please. So I'll just briefly tell, I have amazing collaborators, scientists at Stanford, at MIT, and other places. And we're always incredibly grateful to the students, parents, and schools who are our research partners and participants, and without whom we would learn nothing. And we're so grateful for their volunteering of their time. Thank you very much.
Thank you, John. At this point, I'd like to invite our colleagues in the room to contribute any questions that they'd like. We have a short Q&A period before moving on to our panel. So you gave us much to think about. There are already some questions in the chat, but I would like to invite folks to contribute any questions that they'd like Professor Gabrieli to address. I'll start with a couple that I've seen in there, and there was some reference, much reference to early screening. Can you talk a little bit about at what ages or grades should we be doing universal screening, et cetera?
Yeah, sure. So many schools monitor the progress of their students, but we think that screening at the end of pre-K or at the beginning of K is really valuable, because we're pretty good at knowing who's going to be at risk. Again, the biggest problem is we over-identify, but we miss very few children. They have to be interpreted in the context of the child. And the teacher has to say, like, of course, this child can't read because it's a visual test, so they have a visual impairment. It's not going to be some automated thing. It will require the judgment of teachers and educators who know the child and in the context of the child. But that could launch interventions or supports for children whose pre-reading skills clearly indicate that they're at risk for reading difficulty. We're all in favor of doing that, because the earlier you identify it, here's the key thing, two things. Interventions work best on the youngest children. That's well documented. And the second thing is the social emotional aspect. Many of you know this, but children who struggle to read often are very discouraged. They see their friends, and peers moving ahead of them. They struggle to read. The read alouds, they can be laughed at. The readers, they can tell they're behind on their other students. So we want to spare them this discouragement, which is really, extra pernicious. And so the more we know a child needs a certain kind of help to maximize their reading skill, the earlier we start, the better. So end of pre-K and K, we can do pretty well.
Thank you. There were a few questions with regards to emergent bilinguals, English learners. Can you talk a little bit about what you're finding with that?
Yeah, so that it's such an important topic. I could tell you that much of our research, and this is a huge limitation, has been in English, just because of sort of practical issues, but we're very sensitive to that. So I'm collaborating with a group at the UCSF Dyslexia Center, where we're trying to, and we have a Spanish language version now, and we're working on multiple other languages as well. So we know it's really, really important. And it's been a slow start in many ways, just because it's hard enough to pull off this thing in the scanner, with one kid. But we know that it's incredibly important to be thoughtful and responsive to the variety of experiences and cultures and languages that children grow up in.
Thank you, John. There was a couple of other questions. There's one with lots of scientific language, and I don't want to mispronounce it. But I am a pretty confident reader, so if I make mistakes, it's okay. You'll help me out here. Someone's asking, could you speak to the angular, is it gyrus or gyrus, and arcuate facialis? Are they related or similar in function?
Yeah. Very great question. So we talked about this left arcuate fasciculus. It's a fancy set of words. It's this white matter pathway that connects the major language areas of the brain. And so the angular gyrus is at the sort of the edge of the parietal cortex and the temporal lobe. We think that's a really important spot for where children match the sounds of words with the look of print, which is the essence of learning to read. Children arrive, speaking and hearing language, and now they have to figure out how do they attach that to initially meaningless print. It's an amazing thing. And so there's a fair bit of input to that fasciculus from the angular gyrus. So it's a great science question that these things are very much involved in the same system of language initially, and then applying language to print.
Thank you. I'll have to give credit to Tara for that question.
Okay.
Also, I think I've been seeing some contributions and questions about effective programs or approaches that you have seen or read about or studied.
Yeah, one source I like is the What Works warehouse, from the U.S. Department of Education. That's a good place to look. There's a number of different programs. I think the biggest thing, as a researcher, I like ones that have some randomized control trial, RCT, randomized control trial evidence, so that you really know if it worked or not. Of course, there's different contexts, but or some things work and some don't. And almost all of the ones that will have the common property that they really focus on explicit instruction about the relationships between sounds and letters, or what people call phonological awareness, because that's the best understood and the most common difficulty that children have to crack the code of print. But there's variation amongst children, and we have to learn how to approach that. And we know, again, that even the best interventions can work for a significant number of children, but are less effective in others, and we need to understand what's different about those children and what will work instead for those children.
Thank you. There is a question about how your research is informing curriculum development.
Yeah, honestly, I don't think, we just have a small part of a big story. The big story is the people who develop new curricula and most of all the teachers who implement it on behalf of children. And so I think, people have said, like, what is that right hemisphere thing that's happening in kids who make the most progress? Can we target curriculum at it? That would be really cool. And we don't really know that yet. I mean, one of the bad things about science is quality science moves really slowly compared to the needs of children, parents, teachers who need today to do something on behalf of children. So I know that. And we do the best we can. And so it's really exciting for me to work with the UCSF Dyslexia Center, Florida State University, and the state of California on, for example, a screener, because I can imagine that would be tremendous. I'm hopeful that will be tremendously helpful to many children and teachers in schools.
Thank you, John. There was a question about that UCSF project, the phenotyping. So if you want to speak a little bit more about that, but there is a question that's about technology and your opinion about, do you think technology or video games is affecting students' ability to develop phonological awareness? Or what role?
So I'll be slightly radical here and say that, it's shocking how technology has had very little positive influence. I know we worry about other things. I'm not going to talk about social emotional things on Instagram right now, and so on, a distraction of video games instead of reading a book. But in terms of classrooms, I think that the desire to market technology has been honestly way ahead of the evidence about which kind of technology was really helpful. So I think it could be amazing. It could be highly personalized. It could fit individual children, instead of with one teacher with 20, 30 children, maybe the software can be more individualized. But the values of saying we really want to know if something works before we buy it for a classroom have not been as strong as I wish. So I'm a scientist. I always like scientific evidence. It could be my, they say, what is it? A carpenter always sees things they have to nail down, right? And so, maybe I'm like that. But I do think that if we had brought more of a evaluative approach in technology, what works and what doesn't, we would start to sift through that and then tell teachers and tell children and tell parents, oh, this really works. But right now, everybody's flooded with a lot of technology with very little evidence that it enhances outcomes.
Thank you. I think we have time for maybe just a couple of more questions. So please feel free to contribute in the chat. But is there anything that you'd like to kind of highlight or reinforce? I know there was a question early on that you wanted to address a little bit later.
Well, I just want to say that I just think I'll just say, I really want to congratulate Todd and all of you. I saw the comments that people had coming out of the chat rooms and stuff like that. And it's just so inspiring. And the fact that you're spending your day on this, thinking about this, you're building a community that wants to improve reading outcomes for so many children. I feel like sometimes, like, education is so complicated, our society is so complicated, economic issues, social issues, and so on. It feels like if we can't, as a group, get this one right, initial reading in the school, it's a relatively finite problem, but it's a power for children, throughout all their years, in school, after school. So, it feels to me like such a noble thing that you're inspired to work on. And it's, the passion of such a large coalition that will make all the difference. So I'm just so honored to participate in this and, hopefully give you a bit of information that was useful. Certainly, all the brain evidence says early screening is incredibly important. And then early intervention is incredibly important, because we know we can make a difference on behalf of many children. As you move into the higher grades, things get much more complicated, and we still have to teach effectively, but it's a highly doable thing with a lot of effort and a big coalition as you're building. We can make a tremendous difference on behalf of so many children.